Hey guys, today we are going to continue talking about exponential and logarithmic functions, and today we're actually going to be graphing them. And the easiest way to graph an exponential or logarithmic function is using transformations. So let's review what an exponential function looks like. So exponential parent function. Interesting thing here is that there's no official exponential parent function like we have y equals x and y equals x squared, all those. Our parent function would be y equals b to the x power. So that's kind of hard to graph because I don't know what b represents. So when you graph an exponential and you think about the parent function, you just kind of put a number in for the base. So I'm going to start with something straightforward like 2 to the x. So when you're graphing this guy, it would be really easy to just make an xy chart for yourself and plot some points. So you know anything to the 0 power is 1. We would know that 2 to the 1 power would be itself. And we could just keep making points here. I don't know why I skipped 2, but 2 to the third is 8. And so I could get my graph started here. So if I go ahead and I plot some points on here, 2, 3, 4, 5, 6, 7, I'll just pretend like that went up to 8. We'd have this point 0, 1, we'd have 1, 2, and then we'd have 3 all the way up to 8. Now the question is what's happening when it gets smaller, when x is getting tinier. So if I plug in a negative number, we remember a negative exponent flips over my base, and so I'd get negative 1 and then 1/2, and it would just get progressively smaller. Now when we connect my dots, the one thing that's important here is that my graph never actually touches the x-axis here. We have, just like in a rational, we would have this guy as a horizontal asymptote. You can't, as x is getting closer and closer to negative infinity, it's getting closer and closer to 0, but it never actually hits that. So we'd have a horizontal asymptote at y equals 0. Okay, and so there's some couple important points that we could get just from this graph. And that is that any exponential function is going to go through the point 0, 1, because anything to the 0 power is 1. Another important point up here is that we always go through, if I have the first power, it's going to be whatever that base is. Okay, and then we have that horizontal asymptote at y equals 0. So this is true if b is greater than 0. So if b is, greater than 1, that would be true. We'd have that graph that's increasing. So again, and our parent function always goes through these important points. Through 0, 1, and then 1 comma your base, and then it has that horizontal asymptote. Now the only problem then is what happens if you had an fraction in your in your base. So if I had this guy going on here, again you could make that t-chart, but you remember here that we'd still be going through 0 comma 1, and then we'd have to go through my base, or 1 comma my base. I'm just struggling with words today. So 1 and then 1/2. And so knowing that, we're going to have this type of shape where it's decreasing over time, and I didn't actually hit that point. So as x is going to infinity, it's kind of that limit notation, y is going to 0. So the only thing that changes when you have a fractional base is that you're decreasing instead of increasing. Okay, it still goes through those important points, still has that horizontal asymptote, it just goes a different direction. Okay, and so let's kind of remind ourselves of some important transformations here. So the first one I'm going to start with is a vertical transformation. If you have b to the x plus 1, 1 is not in the exponent, it's out to the side. We remember that that's going to be a vertical shift, and because it's a plus in here, it goes the direction I think it's going to go, so it would go up 1. Now if I was to take this and do this with a regular function, I would take whatever that point was that I graphed and I would just add 1 to it, to the y, because it's a vertical shift. So you're going to add 1. Okay, now if it's up there in the exponent, your plus 1 is hanging out with the x in the exponent in the argument, that becomes a horizontal shift. And this is the one that's really weird because it goes opposite of what you think it's going to go. So if it's a plus, it's actually going to go to the left one. And in order to figure out what this point would be, you would just take your x-coordinate and subtract 1. And then remember, if we have a negative in front, that's going to be a reflection. So this guy is going to reflect, and because it's up there with my argument, it's a x. It's going to be a vertical reflection. But that's kind of weird because what's going to happen is it's actually going to reflect over the y-axis if it's flipping that direction. So all you've got to do here, and that doesn't really make sense for this box, is you're going to take your x-coordinate and you're going to make it negative. So then x is by the negative sign, that's when you're the one you're going to make negative. Okay, same thing works if you have the minus. This is just a vertical shift, and instead of going up, it'll go down. And then again, you take your y-coordinate, subtract 1. If it's up there in the argument, then you're going to have a horizontal shift. It goes opposite of what you think, and then you're just going to add 1. Okay, and then finally, this one is going to be a reflection over the x-axis. And then it is going to just take that and you're going to change your y-coordinate. So let's practice doing this for a second. So there's your table kind of filled out. So what we're going to do here is I'm going to think about what is my parent function. So my parent function for this particular guy, if I was going to try to graph it, would be 5 to the x. And we know that the parent function always goes through those important points. So it's always going to go through 0, 1. It's always going to go through 1 comma the base. And it's always going to have that horizontal asymptote at 0. And so I'm going to change this and make this 5 because that was what my base was. Okay, so if I go ahead and I think about what's actually happening here, I have a plus 4 going on, so I have a vertical shift and it's going up 4. So I'm going to take all of those y-coordinates and I'm going to add 4 to them. So my new function is going to have a y-coordinate here of 5, an x-coordinate, or sorry, a y-coordinate here of 9, and then since I'm shifting up, this guy is actually going to shift up to 4. Okay, then I look at my other part, I have a horizontal translation, horizontal shift, and remember it goes opposite of what you think, so it's actually going to go to the right, struggling there, and I'm going to add 2 to my x's. So I'm going to take my x, I'm going to add 2, going to add 2, and then that doesn't matter for my horizontal asymptote. So then I just got to plot those points that I just got, so 1, 2, 3, 4, okay, tried really hard to get that. So that's 2, 5, 3, 9, and then I have that horizontal asymptote happening at y equals 4, and then I just try to connect my dots. Ooh, that was bad, but I tried. Okay, same deal if you have any sort of reflection. Because the negative is outside your base and not up in your argument, it's reflecting over the x-axis, so you change your y-coordinate. So again, your parent function has those points, 0, 1, 1, the base, and the horizontal asymptote of y equals 0. Your new function, you're just going to change all your y-coordinates. So you're going to have this one become negative, this one become negative, and then you're not going to change anything about your asymptote because that can't be negative. Okay, plot those points. So I would have 0, -1, 1, -3, and that would be what my graph looks like. Okay, so let us go ahead and switch gears and talk about the logarithmic parent function. Same idea here. And when you look at this, we're again not going to have an official parent function. We have log base b of x. So we can plug in whatever number we want there as long as it fits our log rules. So if I go ahead and I think about plotting some points here, again, we're going to find some important points. And I know if I take log base 2 of 1, anything that is going to have that 1 in the log, it's just going to be 0, okay? Because what you're asking yourself here is 2 to the what power gives you x? Well, 2 to the 0 power would give me 1 if I plug in x as 1. Okay, we also know if I plug in 2, log base 2 of 2 is 1. And if I get bigger, maybe like 16 or 8 or one of those, we ask 2 to what power gives me 16? Well, that would be 4. So then I go ahead and I can plot those points. And I have 1, 0, 2, 1, and then I have a really big x up to 4. And so I get this shape going on. And again, if you think back and you're trying to figure out how to graph this thing right here is going to be the inverse of the exponential parent function. And basically all that means is that you're switching your x and y's. We did this back when we did inverse trig, or you're mirroring over the line y equals x. And so the one thing to remember here is I can never take the negative argument of a log. So that means that I can get close and close and close to x, the y-axis, x equals 0, but I'm not actually going to touch it. So this guy, instead of having a horizontal asymptote, is actually going to have a vertical asymptote at x equals 0. Okay, and it also has those important points as well. Except for now, you flip-flop them. You're going to have 1, 0 is always on a log graph. You're going to have your base, 1 is always on the log graph. And again, that's just flip-flopped from your exponential. Okay, so that's all you got to know for that. Either remember your exponential and know that it's a flip-flop, or remember those special 3 points that are always going to be on that log graph. Okay, so I have no idea why there's 2 graphs here. Let's talk about some transformations. Okay, they work exactly like you think they should work. So if you have a +1 inside your argument, we know that this is going to be a horizontal shift, and because it goes opposite of what you think, you're going to go towards the left. And so again, you're going to take that x coordinate and subtract 1. Okay, if it's outside your argument, so it's going to be very obvious if it's outside, it'll be a vertical shift, and this one does move the way you think it's going to move, so I'm going to go ahead and just take y plus that number. The negatives are where it gets a little bit tricky. Remember, if it's inside, we're going to have that reflection where we change all of our x's. We change our x coordinates and make them negative. Whereas if it's outside, we're going to have that reflection where we make all of our y's negative. And so these are going to be the same type of process when you try to graph them. We're going to have the same process. So what I'm going to do here is think about what my parent function would have in it. So my parent function always has those points, 1, 0, the base, which is 2, 1, and then it has that vertical asymptote at x equals 0. If I look here, I have a negative outside my function, which means I'm going to change all my y's and make them negative. So my new function is going to have 1, 0 still, because I can't make 0 negative. 2, -1, change my y's, hello, and then again I can't make x negative, so it'll just be 0. So I'm going to have the same idea going on here. I have that vertical asymptote, I have 1, 0, but now I have 2, -1, which means all I've done here is I flip-flopped my graph. Okay, and then again, if it's inside, this one is the one where you're going to change your x coordinate. So if your parent function was 1, 0, 2, 1, and x equals 0, your new function on this guy, you're going to change all the signs on your x's. And again, you can't change the 0, so we're just going to leave that one alone. Wow, that was so not on the line. I tried. Okay, -1, 0, and then -2, 1. And so again, this one flip-flopped over that y-axis. Okay, the last thing that we need to talk about as far as graphing functions is finding the domain of these types of functions. Okay, domain is pretty straightforward because domain is always based on the argument. And so if I think about something like a square root, you couldn't have a negative square root. If I think about having a rational function, we know that we couldn't have that denominator be 0. But if I have a log function, that same rule holds true because we know we can't have a negative in here. We couldn't have that negative and we couldn't have that be 0. So the domain is based on the argument, or what's inside the parentheses, and this can't be 0. Or sorry, negative. I don't know what I'm trying to do. I'm trying to get ahead of myself, so what's happening. So I'm going to take whatever's in my argument, so whatever's in those parentheses, and I'm just going to take that, and I'm going to set that bigger than 0. Because I know that that's going to be the point where it changes and turns into that asymptote. So I go ahead and I solve this. I'll subtract 6 from both sides. Hardest part here is to remember when you divide by a negative, you're going to have to change the sign of your inequality. Whoa, struggled with words there. To flip your sign. So now I know that in this case, x has to be less than 3. And you can write it like that if they wrote it in interval notation. Remember that if it's less than 3, we include all the numbers from -infinity up to 3. And remember, there's no line underneath this, so I would put the parentheses there because that is a vertical asymptote. Okay, that's all I've got for you today. I will see you tomorrow.